And so really the cranial direction, the surface is able to engage the soil more, to shear it more, to dilate it more. And that's why we see those greater strengths. Now, it's important to recognize that in the field, for certain conditions, for example, for piles and soil nails, the state of stresses is actually linked to the dilatancy. And so there's a very simple model we use in the laboratory. It's the constant stiffness model, where this is in a top view. So if we have a pile, the far field soil, we represented by linear springs. And the springs have a stiffness K that depends on the shear stiffness of the soil, G, and the diameter of the pile, D. If we look at the pile on its side, so this is the pile, we have the soil, it may be dilating, and so then we have a normal stress that could change, and that change is linked again to the spring stiffness. Over here, we're showing the soil as a soil element that also has a normal stress that can change according to K. In this model, the current normal effective stress is described as initial with the added contribution of the dilatancy delta times that spring stiffness. So that's what's shown here. So we went back to the lab and we performed these types of experiments. Now, to look at the strength, tau, we need to remember that the strength depends on the effective stress and the friction angle. And so we see the test in the cranial direction has a much greater strength than the caudal direction. I had already showed that in the cranial direction, we dilate more than in the caudal. But what changes now with the constant stiffness boundary is that the normal effective stresses increase more in the cranial direction than in the caudal. So now we have two contributions that lead to this large difference in the strength. And so now we can conclude that the friction angle is greater in the cranial direction, as well as the dilation, and also the changes in normal effective stress. And again, we have verified the strengths with different sands and different boundary stiffnesses. And so what we can do now that we understand this a little bit more is start playing with the cyclic loading. And what I'm about to show are load control tests. Where what I'm going to do is I'm going to cycle at a constant amplitude, and then I'm going to observe how many cycles it takes to fail. And I'm going to fail due to the inability to mobilize that amplitude. And if I have this asymmetric failure envelopes and my load is symmetric with an average of 0, then I should always be failing on the caudal side. And so let's look at a test. Here, I'm starting in the caudal direction and then cranial. So caudal, cranial, until I get a pull-out failure in the caudal side. The soil contracts little by little, progressively, and then I end up having that failure. And the stress path that's shown here shows a decrease in the effective stress. And I get that decrease because now I'm linking dilatancy with effective stress, until I touch the failure envelope in the caudal side, and that's where I get this pull-out failure. We can do the opposite test to look at whether this is direction dependent. We do cranial first and then caudal, cranial, caudal. We get a failure in the caudal side that comes from all the contraction that decreases the effective stresses. And again, the failure comes when we reach the failure envelope in the caudal side. And so with this, we conclude that if we do symmetric loading, we should always be failing in the caudal side. We can now start introducing a bias. And so what we do here is we introduce a bias towards the cranial side, because we want to test how much bias does it take to fail in the cranial side as opposed to the caudal. And so that's what we did. We started with a bias of 10%. And so we shear caudal, cranial, but now the cyclic amplitude in the cranial side is greater, as we see here. We accumulate much greater displacements, but we end up failing in the caudal side, as shown here. And that's because we touched the failure envelope in the caudal side first. We can bump that up a little bit and increase our bias to 15%. we continue to accumulate displacements, but now they're all in the cranial side. We get more contraction, and we finally get a failure on the cranial side. And so from this series, what we learn is that it takes a bias of somewhere between 10 and 15% in the load to be able to fail in the cranial side. Otherwise, we're always going to be failing in the caudal side. That's the weaker side. So some takeaways from this: the interface friction angles are greater in the cranial side by about a factor of 2. The asperity height and length has an influence on the mobilized strength. The cranial shearing led to greater deformations in the soil, as shown by the PIV analysis. And also, the cranial shearing led to greater increase in the normal strength. Then under symmetric loading, we always fail in the caudal side, and that's because the failure envelope has a smaller slope, and a load bias of 15% led to failure in the cranial side. Moving on to the skin friction directionality in the piles. Oops, sorry, my light turned off. We went to the centrifuge. We used the 9-meter centrifuge at the Center for Geotechnical Modeling at UC Davis. Here's a picture of the centrifuge, and this is a picture of our setup. And we use the centrifuge because it allows producing a stress, magnitudes, and distributions that are representative of field conditions. Again, we wanted to assess this in conditions that are closer to those in the field. We used the 30G acceleration on dry, poorly graded sand, and we installed the piles in flight by quasi-static pushing. And I'm going to focus on monotonic loading today, and I'm going to present all of the results in dimensions that are in the prototype scale. These images show our piles. They have a prototype length of 10 meters and a diameter of 0.6, and they have 5 internal strain gauges, and you can see the cables here. We have 5 different textures. This one pile we installed cranially, and so you see how the sand particles would encounter the sharp edges. We also have the pile that we installed caudally with 2 different heights of the asperity, 0.3 and 0.72. We have a rough pile and a smooth pile as well for comparison. I'm going to show diagrams of load distribution with depth. On the right, I'm going to show the loads during installation, and on the y-axis is the depth. And this is color-coded. So red is the rough pile that mobilizes the greatest loads. As we would expect, the surface roughness is greater, so the strength is greater. And the smooth pile shows the smallest loads. Now, the pile in dark green, that's the one I installed cranially, as shown here. It mobilizes very similar loads as the rough pile, and the other 2 piles mobilize loads that are smaller, closer to the smooth pile. Well, now what happens if in the same test, now I do a pull-out test? As we would expect, the rough pile is very strong, and the smooth pile is very weak. The pile that I installed cranially, that's this one, that took similar loads during installation, now it's significantly weaker than the rough one. And then the other 2 piles that were easy to install now become the stronger piles, particularly the one in purple with the higher asperity. So now we're seeing on the centrifuge this concept of frictional directionality. It's harder to pull these piles that are loaded cranially in the pullout. So taking a closer look at those 3, the rough pile, on the solid symbols, I have local shear stresses during installation. And in the open ones, I have local shear stresses during pullout. And so the ratio of those, tension to compression, is about 0.4. The pile that was installed cranially has very large local shear stresses, much larger than during pullout, and the ratio is about 0.2. And finally, we have the 3rd pile that was installed cranially, and now we see that the pullout local stresses are much greater than the installation one, and the ratio now is 1.4. We can now take a look at the local TZ response in terms of shear stress and head displacement. Just showing, I want to focus on the cranially pulled one, how the mobilization of shear stresses is much greater when we pull in the cranial direction than this one in the caudal direction. And again, this is not only because of the friction angle. The friction angle is greater on the cranial side by about 2, but this actually has a lot to do with increases in the normal effective stress. So some takeaways from this is that the skin friction and its distribution with depth depended on the direction of loading. While the friction angles are different, a lot of the difference really comes from the increases in the normal effective stress acting on the pilot. The normal stress is increased more during cranial shearing. We've also performed cyclic tests, and we're starting some plans to do some field tests on prototype pilots. I wanted to show some quick results on our recent field tests. We performed tests on 2 sites on poorly graded sand and silty clay. And this is the rig that we used. We pushed to different depths, 2.5 and 6 meters. We tested all in cranial pullout. And here you can see a picture of our soil nail. So you can see how we're installing it with the rig, and then we're gonna pull on it, and we're gonna measure the cranial direction. And we changed the length and the height of the asperities here. Just to show some results, the trends actually matched those in the laboratory as well as those in the centrifuge, which mean that the pullout was very high. The stress ratios as high as 12. So these are very high values, particularly for the tall asperities of 4 millimeters, as shown here. As we decreased the height of the asperity, the strength decreased. We also had a reference rough soil nail that mobilized the least resistance. And also, as we decreased the length, we also decreased the capacity of our soil nails, as we see here. And so again, the trends we saw in the field also match those that we saw in the laboratory and in the centrifuge. So just to close up, we saw that the asymmetric profile mobilizes this directional dependence on many aspects: the strength, the latency, local soil deformation, cyclic degradation. Pilot tests showed similar trends with greater skin friction in the cranial direction. And those trends were very similar as well in the field test on the soil nails. There's other work we have performed on interface shear behavior in clay soils, or behavior with surfaces with compliant asperities, cyclic loading, centrifuge, as well as some biological analysis of the snake skin scans. And I think we're getting close to the time, so I'm gonna just jump to the acknowledgements to really acknowledge all the contributions from the students that have been doing all the hard work here, as well as collaborators that we have worked with throughout the years, as well as the funding agencies. CVVG, that's an NSF center, as well as the Center for Geotechnical Modeling. And with that, I just want to say thank you again, and I'm happy to answer questions if we have the time.
Thank you very much, Professor Martinez. Do we have any question for the presenter? If you want, you can write it in the chat, or just raise your hand, or just directly ask the question. We don't have any question, I guess. I was going to ask you, have you tested this in different types of soil, like clays or the interface by shape?
Yes, we have done, I would say 90% of the tests we have done are in sands. And so everything I showed today was for sands. For clays, we've done some tests in the laboratory that also show this frictional directionality. Although the magnitude seems to be a little bit smaller than in sands. So the difference between the cranial and the caudal seems to be different. It's slightly smaller than in the sands, and it also depends on the over-consolidation ratio. It's and there's instead of the density, we have the OCR that also plays a role there. But it's something that I think should be looked at further.
Okay. Do we have any other question for our presenter?
I see a question in the chat from Professor Raul Fuentes. He's asking, if the mobilized interface friction angles compared, or how did they compare to the sand angle of friction. In the laboratory, they were for the surfaces with the tallest asperity, they were pretty close to the internal friction angle of the sand. In the centrifuge and in the field, we can't really compare because we don't know the magnitude of the effective stresses. But at least in laboratory, we see that kind of an upper bound appears to be the internal friction angle of the sand. Now, I think the dilatancy can be a little bit different. And so them having similar friction angles doesn't necessarily mean that they have the same strength, because in the field, the normal stresses depend on the dilatancy. And so we actually think we can force the soil to dilate more with these types of surfaces than with just a rough surface like concrete or something like that.
Any other question? No? So thank you very much, Professor Martinez, for your presentation. We move on to the next presentation.
Recording in progress.
Dr. Zhang. Dr. Zhang is senior scientific staff at the Institute of Geomechanics and Underground at the Aachen University, and he obtained his PhD at Polytechnical University of Catalonia in 2020. And the title of his presentation is Bioinspired. You can start the screen because we can see here in display settings. Perfect. So whenever you're ready, Dr. Zhang.
Thank you very much, Luis, for the introduction. Hello, everyone. My name is Henning Stutz from RWTH Aachen University in Germany. And today I'm going to give a talk with the title of Bio-Inspired Self-Boring Proof in Shallow Granular Materials. I have changed the title a little bit in order to better align with the theme of the workshop. Okay, so in this presentation, you will see the creation and performance of a bio-inspired self-boring robotic probe in granular materials using the discrete element method. So basically in this presentation, you will see how a probe that is able to do self-boring inspired by biology, by animals, is created. So self-boring means that self-boring probe means that the probe can go into the soil by itself without any connections with external resources. And also in this presentation, you will see how the granular material, which is sand in this case, is simulated using the discrete element method. And in the end, you will see the performance of the self-boring probe and also some engineering implications. Okay. So as geotechnical engineers, we have to go into the soil, even it's very dirty, but we have to do that. We have no choice. And clearly our ancestors are clever enough to invent diverse apparatus to go under the ground. And we take the example of in-situ testing methods. So here you can see there are already quite many in-situ testing methods that have been invented and applied, such as CPT, SPT, and many others, as summarized here by Manner et al. In 2009. And the journey of going into the ground doesn't stop, and it continues. In very recent years, boron mechanism inspired by resin claims have attracted particular attention of researchers to develop a new generation of self-boring probes. And so here you see this is a resin claim, the animal that inspired the researchers to develop a new generation of self-boring probe. And you may think that the world of biology is very complex and mysterious, but But actually, the boring mechanism of clamps is very simple, as illustrated by this diagram here. So a clamp body contains a shaft and a tip. And at the beginning of boring, the shaft expands to form an anchor so that the tip can penetrate deeper into the soil. And then afterwards, the tip expands to form another anchor, and also the shaft contracts back to its original size so that it can be dragged downwards with the help of the tip anchor. So this is the self-boring mechanism of clamps. It looks quite simple, and based on the self-boring mechanism, we design a self-boring probe. Yeah, here you see the profile of the probe. It contains a shaft in this green part here, a tip cylinder, this blue part here, a tip coin, a neck that connects the shaft and the tip, and also one embedment that extends into the shaft. So this is the initial configuration of the probe, and now self-boring starts. So in the first step, which is a shaft expansion, the shaft just expands readily to form one anchor. And then in the next step, the tip will penetrate into the soil with the help of this shaft anchor here through a distance of delta so tip. And then in the next, the tip will expand to form another anchor. In the next, the shaft contracting in step D, shaft contracts, the shaft will just contract back to its original size. And then in the next step, shaft retracting, the shaft is retracted downwards through a distance of delta zo shaft, which is equal to delta zo tip, this penetration distance obtained in step B. And then in the last step, the tip just needs to contract back to its original size. So this is these are all the self-boring steps involved in one self-boring cycle. And in the next, we can already insert this probe into the soil and just let the probe go into the soil autonomously. A bit about the soil sample. So we use discrete element methods to simulate mechanical properties of Fontainebleau sand, which is acidic sand. Contact parameters of Fontainebleau sand were calibrated against element tests, such as odometer test of Fontainebleau sand. Multi-scaling technique is applied here to generate the soil sample. Multi-scaling means that gradually increasing scaling factors are applied to upscale the particles from the central area to the outer areas. And also the surface is, the top surface of the soil sample is set free to simulate shallow ground conditions, and then gravity is applied to settle the soil particles. In the end, the soil, the sample quality needs to be checked in order to ensure that the sample is uniform. Okay. When it comes to soil robot interaction, 1 or 2 checking criteria are required in each step of the self-boring cycle, as you can see here. For instance, during shaft expansion, target force must be reached based on the soil strength around the shaft, as defined by this C1 criteria. And also another example is that during shaft retraction, the retracted distance must be equal to this penetration distance during tip penetration, as defined by this criteria C8 here. Among all these checking criteria, the most important one is C3, which defines the relationship between shaft anchorage force and the tip resisting force.